So this is based on new information on the new mass spec, which has been released on the AQA website. So some of the information in all the textbooks is actually incorrect. So in the textbooks, they explain electrospray ionization differently to what AQA have released on the website. Now, obviously, you're being tested by AQA, so it's AQA's information that we should be using. So I'm going to go through this different explanation. They've also released some questions which are quite difficult mathematics. We'll go through how to answer those. Okay, so you're probably familiar with the basics of a time-of-flight mass spectrometer. So basically the sample comes in here, gets ionized, then gets accelerated, then it enters the drift region where the particles separate. So the ones with the highest MZ value go the slowest, the ones with the smallest MZ value go the fastest, hit the detector. So initially in ionization, so ionization can occur via two different types. This is just talking about one of them. So this is called electrospray ionization, and it's where liquid passes through a fine hollow needle with a positive charge, which adds a hydrogen ion, creating a positively charged ion. We'll go into more detail on this, but this is the bit which all the books have wrong. All the books say an electron is removed, which is incorrect. And we're also going to talk about the other type of ionization, which AQA seem to expect you to know now. So once they've got ionized and become positively charged, they then go into the acceleration area. There's nothing different to this as to what's in your books. So they're accelerated by negatively charged plates. Okay. They then enter the drift region, so the ions travel through the holes, forming a beam and travel along the flight tube. This is where they separate. And then they hit the detector. So in the detector, the lighter ions arrive first. Flight time is recorded. Ions pick up an electron, causing a current to flow. And finally, this is the data analysis. The computer generates a mass spectrum. So this is a diagram from the official AQA pack they released recently on new information on the mass spec. And it describes electrospray ionization. I really strongly recommend you go to the AQA website, the new spec, and you download this pack with all the new information. So I'll just explain how this works. So what happens is the sample comes in through the needle. Okay, so the hypodermic needle. The hypodermic needle has a positive charge, and as the particles exit the hypodermic needle, by the way, hypodermic just means hollow needle. As they exit the hollow needle, the particles gain a proton as they leave the needle. So it's a proton is just a hydrogen ion. If you think about hydrogen, hydrogen contains one proton and one electron. So if you remove the electron, oops, that's not the eraser, if you remove the electron, then you're just left with a proton. So a hydrogen ion is a proton. Okay, so they gained a proton, so therefore they're now positively charged, they come out as a fine mist, and then they get accelerated, and that's just the same as before. What's really key to the understanding here is the fact that because they've gained this proton, we know a proton has a mass of 1. So whatever sample you put in there, when you get your spectrum, all of the sample is going to have an extra 1 proton. So they're going to have an extra 1 mass. So for example, if you get a peak, say at an MZ of 115, okay, so the MZ is 115, say it's some organic compound, its MR is not 115, its MR is 115 minus 1 because of the proton, so its MR will be 114. Of course, that is providing that Z equals 1, so it hasn't gained more than 1 proton. So if Z is 1, and it gains 1 proton, the MZ is going to be 115 over 1, so just 115. This type of ionization is known as soft ionization. The reason it's soft ionization is because it doesn't actually fragment. Say this was a large hydrocarbon. It doesn't actually fragment it into fragments that we see with the other type of ionization that we're going to see in a sec. However, you would get another peak. You'd still get your M plus 1. So you'd get a peak here just to the right of the molecular ion, which would be the M plus 1 ion, which is due to carbon 13. Oops, let me draw that here. So carbon 13 and also hydrogen 2. So you always get this little peak here, which is due to the natural abundance of carbon 13 and hydrogen 2. I think if you watch my previous video on the mass spectrometer, I go into more detail on these, so have a look at that if you're confused by that. So what would the equation look like? Well, so imagine you've got some ethene. So here's some ethene, okay? So in the ionization section, the equation looks like this, plus NH plus. So we're going to form C2H5 plus. So you can see it's turned into a positive ion, it's gained a proton. So the other type of ionization that you need to know about is on the official AQA website. Again, this diagram is from there, is called electron impact. So this diagram here shows electron impact ionization. So electron impact ionization is actually the type of ionization that was in the previous spec, and you still need to know about it. So the way electron impact ionization works is like this. So the sample has to be in its gaseous state. So the gaseous sample comes into the ionization chamber. Then what happens is high energy electrons bombard the sample. So these high energy electrons bombard the sample. They knock off an electron from the sample, or two occasionally, and then the sample becomes ionized with a positive charge and gets accelerated in the usual way. So an equation might be, say you've got, I don't know, something like some ethene. Okay, so the ethene comes along, okay, gets ionized, so you get ethene plus, it's got a positive charge, plus an electron. So you can see an electron's been knocked off. Now the problem with electron impact ionization is that it's quite violent, and with large organic molecules, say you've got something like C10H22, it fragments them. So you get your mass spectra, it looks like this, and you've got fragments. Okay. Now remember, the Electrospray ionization, you do not get fragments. The issue with really big substances, say you've got something really big, like, I don't know, C50H102, is that this is such a violent process that actually maybe none of it completely survives. So you actually get no MZ. What would be the MR of this? So 50 times 12 plus 101. So this has an MR of 101, so we'd expect to see a MZ value of 701 even. But because this is so big, as it goes through ionization, it all gets fragmented, and actually maybe none of it actually reaches as a whole molecule. None of it reaches the detector, which means, so it means we wouldn't get this peak here. We'd only get fragments, so maybe down here and here. Now, there's no new information released on the drift region, but I just wanted to talk about it before we go into the new mathsy questions that they have released. So, in the drift region, you've got your different sizes of isotopes or molecules. So let's say these are isotopes. Imagine this is magnesium. So you've got magnesium 24, 25, and 26. So what's going to happen is magnesium, they're all going to get ionized. They all gain the same charge. They're all given the same amount of energy. They're all going the same distance. Therefore, the lightest one, the one with the smallest mass, is going to travel faster. If it's given the same energy, it's going to travel fastest. So the lightest one reaches the detector first. We're now going to look at some calculations which take into account these different factors, such as distance, time, so it's time of flight, how long it takes to get there, velocity, kinetic energies, how much energy they're given, and mass. So in the past papers and also on the website, they give you the following three equations. Now, you're not expected to remember these equations. However, you will be expected to use them. So what I'd recommend doing right now is just have a go now. Rearrange this one for V. That's probably the hardest thing it is to rearrange it. And rearrange this one for M. So make M the subject. So I mean, like, may have V, try it now, have V equals whatever it is, and have M equals over here. So pause the video, have a go at that now. So what I do first, we want to get V on its own, so I'll divide everything by M, and I'll also times everything by 2, so it will become 2ke over M equals V squared. And then I don't want it to be V squared, I want it to just be V, so I'll just square root everything, so it becomes square root 2ke over M equals V. So I've now rearranged it for V. Okay, let's rearrange this one now for M. Okay, so first thing we can do is we can get rid of the D, so we can divide both sides by D. We'll move the D to the other side, so it becomes T over D equals the square root of M times 2ke. Okay, let's get rid of that square root, so let's square everything, so we square both sides. So that turns into t over d squared equals m over 2ke. Okay, so we want m on its own, so let's just times everything by 2ke. So that gives us 2ke times t over d squared equals m. So here you go, here's one of the real questions which expects you to be able to sort of rearrange those equations. So it says you've got two different equations, and it says show how these expressions can be used to show the time of flight. So pause the video, have a go at this one. A lot of you might be very confused by this. I mean, what do they mean by show these expressions? And this is sort of a maths question, and that's what they're doing recently. They're trying to be sneaky in maths, so those who don't do maths might find this quite confusing. So what we're trying to do is we're trying to take this equation here and this equation here and turn it into this equation here. We're proving this equation. So let's start off with this one here. So what we need to do is we need to see what the common thing about these two equations. So this one's got t and d. This one hasn't got t and d. That's not common. This one's got v and this one's got v. So there's our sort of common thing. So if we make v the subject for this one, we can then put it into this equation. And we can have t equals d over whatever this equals, so we can basically remove v. See, there's no v in here. So first we need to make v the subject here. So we did that in the last slide. We made v the subject, so v equals, so I want to times by 2, so 2ke. I want to take the m away, so I divide by m, and get rid of the square, so I have to square root the whole thing. So there's our v, so that's what v equals. Equation t equals d over v. We know what v equals. We've got v in green and red here. So let's just put all that in the place of v, and then we'll give out this equation. So let's check that works. So here we go. So I've got t equals d over the square root, and then put the stuff in green, 2ke over m. Oops, that m's rubbish again. Over m. And you'll see, hang on a minute, that's not the same as that. Well, now we have to do a little maths trick. Okay, so you can see that we are dividing d by the square root of 2ke over m. What you can do, when you divide something, it's the same, when you divide something which is also a division, it's the same as multiplying it, but you flip the denominator and the numerator. So let's do, we've got d equals times the square root, and because we're putting it times, we have to flip, so m becomes on the top, and the 2ke goes on the bottom. And there you go, we've now got to this equation. So to get the marks here, you have to go through these steps. Obviously, you're proving this equation by adding these together. You need all of these steps to get there. So pause the video and have a go at this question. You'll be given, in the previous question you were given these two equations, so you won't need to remember these as I mentioned before, but these are the equations you'll be given. Use these two equations to work out the answer to this. So you're working out how long would it take to travel along the same flight tube. Right, so hopefully you've tried it yourself, so we're working out time, okay? So we are trying to work out time. Well, do we have d and v? Let's have a look. Well, we've got d, so d is here, 0.8 meters long, but we haven't been given v. Well, we can work out v if we rearrange this equation. So let's put in d first. So we know that t equals 0.8, that's from there, that's the distance over v. So all we need to do is work out v and we can work out t. So let's rearrange this equation for v. Right, so we've got v equals the square root of 2ke over m. So do we have ke? Let's have a look. All ions were accelerated to have kinetic energy. Yes, we've got kinetic energy 1 times 10 to the minus 16. Do we have m? So m is mass. So there's our mass. Yes, we got m in kilograms, and that's the right. Oh, by the way, that's a very important point actually. This mass here is in kilograms, not grams. So, for example, if you in a different question, if you had to work out mass using mass equals Mr. Moles, that would give you an answer in grams. So you'd have to convert it to kilograms to answer this question. But in this question, they've already given it to us in kilograms, so that's fine. Ke equals 2 times where was KE? Oh, there it is up there, that's it there. There's KE. So 1 times 10 to the minus 16, oops, I'm doing 6, okay, over, and then M, we've got M, which is 1.079 times 10 to the minus 25. Okay, be really careful when you throw this into a calculator. And what happens if you put this into a calculator without using brackets here and here, and basically large brackets for this whole point here. What I mean by that is when you put it into the calculator, it must contain large brackets around this. If you don't put large brackets around that, what it will do is it will square root the top first and then divide it. So you'll basically get the completely wrong answer. So you've got to put these two, this division has to occur first before the square root. So one way to do that is do this division first and then press square root answer, or put these large brackets around the whole thing. If you've just got brackets, say, around these individually, that will not work. So that comes out on my calculator to 43053. Okay, and that's our velocity in meters per second. Okay. So we'll throw that into this equation here, so 0.8 over that. Okay, so that comes out to 1.85817 times 10 to the minus 5. But the question says give your answer to the appropriate number of significant figures. So that is not, that would lose me a mark putting it like that. So what I need to do is I need to look at the data and work out what is the appropriate number of significant figures. So that's to 4 sig figs, that's to 4, that's to 4. But hang on a minute, that's to 2 significant figures. But think about it, are you actually using this value here? Well, we don't actually use this value 65, so therefore the only values we actually used are the ones which are all to 4 significant figures. Therefore our answer must be to 4 significant figures to gain the mark. So this becomes 1.858 times 10 to the minus 5 to 4 sig figs. Now there's actually some more to mass spec that I probably want to cover, but this video is getting really long, so I'm probably going to do it in a different video.